Okay, so today we are going to start talking about actual answers. Up until now, we haven't gotten a single answer in this course. So today, we're going to introduce an actual material, and by the end of this course, we're going to be able to say, yes, this particular member works, or no, it does not work. Before I do that, I want to address two things. The first one is, I get it that you guys are feeling a little bit overwhelmed right now. The beginning of term 2, or I guess it's term 4, the second term in year 2, is always a little bit overwhelming in January and February. You guys have a lot going on. I'm not trying to make it harder on you by any means. I can tell you that I do find this is the same course and outline and kind of workload that we have every year, and I can tell you that somewhere around now, the students kind of breathe a sigh of relief. Even though the equations start to look really terrifying, there's answers. And they can say, okay, here's what we're doing from beginning to end. And it all kind of comes together and crystallizes. So we're right there. You're going to start seeing why we bothered with so much of this other stuff. I know until now it's been frustrating, but it's such a linear process. Everything I've been teaching you is that everything we have to do to ever get an answer for any single one beam or column we design. So everything we've done until now, and will do until the end of this term, an engineer does 1,000 times a day. Now, that's not to say, whoa, poor begone us. It starts to get easier as you do it more and more. But I want you to understand the process that's happening. And that's really what the mandate of this course is that you understand why these things are linear. It also means we can only teach you it in a very linear way. But we're going to start to get answers. The second thing I want to address is course evaluations from last term. I know not all of you were in the course. I find the course evaluations very helpful because it lets me address things you guys might be struggling with. This year especially, where we had to switch to an online platform, there were things that we didn't even know how to handle. The first one I want to talk about is my availability. Now, I get it. With an asynchronous course, it's kind of hard to set up anything where we have interaction. I try to be very prompt on email replies. If I can reply to it within a day, sometimes it's an hour if I can. Now, I know I always stress communicate with the TAs first. There is some very important reasoning with that. One is that when I was in engineering, you never talked to your teacher. You talked to your TAs. That was the only person you talked to. If you needed something from the teacher, the TA went to the teacher for them. So maybe I'm adopting some of the methodology that is standard in kind of the engineering discipline, because we are doing an engineering course. That said, I'm not cut off from you guys. If you guys have something you want to talk about, if it's something that's not appropriate for the TA to deal with, I'm here for you. The second is that sometimes trying to formulate your question to the TA really kind of helps solidifies the question. And I find that a lot of time people end up answering the question themselves. So and if you can answer it yourself, there's a real process there that helps lock it into your brain. So the reason this kind of system is set up is that you guys come up with your question. If you don't understand something, you reach out to the TA, and the TAs are a very important part of this process. You know, they're there for this. That's why the administration brings them into this. And then if you guys can't answer it together, then come on to me, and I am more than happy to help out. Last term was really weird because of everything going on, where they were the administration was overrun. I felt so bad for them. They didn't give me the TAs until the third week of September. We were well into our third week. But we have to set up some system of how things work. So I had already had to implement everything before we were even given the TAs. People did reach out to me about this issue at the end of the term, and it was a very valid issue that TA accessibility was almost impossible, simply because there was no platform for it. There was no tutorial. So this year, or this term, I set up with the TAs, and you guys have seen this, that you have two 2-hour time slots throughout the week. They've been working, they aren't given your schedule, which is a little bit weird, that they had to kind of troubleshoot and find time slots that worked for you guys, but they're available for you guys kind of in a real-time forum if you find it easier to communicate that way. But they're also available by email the same way I am all the time. So that was a big one that we tried to address as well. So you have 4 extra hours a week of dedicated communication time should you use it. Sound quality in my recordings. I mean, I'm doing the best I can. They don't give us anything. We're just working with our own tools. They didn't give us any information. I had to figure out all of the technology that we're using to do this. There was no here, do this to make your lectures accessible and usable. So I've done a lot of internet research on what I can do. I can look at buying a better mic. That might help. Some of it is just lag time that I'm trying to run, the video recorder, the slideshow, and a few other things all simultaneously. So, I have an expensive, fancy computer because I'm also not while I'm recording, but running, very complicated software for the analysis that I'm doing. So I don't know what to do beyond that. I'll start pricing out mics and see what I can do for sound quality. The last one was somewhat upsetting. Someone complained about my children appearing in the lectures. They said it was unprofessional and disrespectful to you guys. I can feel myself flushing and getting a little bit upset. We're all in a pandemic together here. We're all trying to cope with this together. I am in my house with 2 small children, 24/7. They've put a lot of stress in the department about diversity and equality. I am certainly a very privileged individual as a white female, so I certainly cannot say that I feel the oppression that many people do, and I sympathize with you. I can't understand, but I'm here. But I am a female in an industry that does not have a very good success rate with women in it. Architecture has very few principals of firms, simply because, I'll get to that in a second. And in engineering, the statistics are even worse. I can think of 0 female partners at major firms. The only women I know in engineering that are head of firms are ones that started their own firm. So there's a real kind of difficulty in advancement there. And one of the things, and I'm not going to say it's the only thing, but one of the things is that the burden of child rearing falls predominantly on women in our society. I have a wonderful husband who I love very much, but I will say in our household, the majority of the child rearing falls on me. If you have a problem with my children appearing in these videos in a pandemic, when there's 4 of us in a house, I'm teaching in my dining room. My husband's in the nursery on a conference call. I had to install a doorway between our kitchen and our living room to keep my kids on that side of it as much as possible, while they're doing video lectures as well. You have a problem with them sometimes appearing. I don't know what I can say to you, but too bad. So many of you, I have to say this, so many of you have been so wonderful and so understanding and reaching out to me to just say that you appreciate what I've been trying to do. So my kids will periodically continue to appear. It's usually for a very small moment, but I am in my home. Now, if your big worry was distractions, I can tell you that if we were in a classroom, we would be having the same issues. One year they were doing construction in the classroom above, and I would have to pause for 5 minutes at a time as they started to drill into concrete. So if that's not a distraction, I don't know what is. There was the time there was no heat in our classroom and we still had to give our lecture. There was the time that the entire video display didn't work and everyone had to manually download the lectures so that we could follow along on our screens independently. So there are always going to be distractions in any situation, whether we're live in class, live on video, or recording like this. And I'm not going to apologize for those distractions. It's part of my life. It's part of the way that we can make this work. You know, when I signed on to do all of these lectures this year, because this was a year that I went from 3 courses to 5 courses, it was pre-pandemic. So it's not like I signed up for this knowing this was going to be the situation. That said, I want to do the best I can. I want to make it easy and accessible for you guys. Other people have also said that they don't mind the small, insight into life. It makes it human. It makes them reach out to it. And if you are the person who wrote that, I'd be curious to know if you've ever eaten while you're watching my lectures. There was also a complaint that I ate peanut butter toast one time. I was really hungry. I was very tired and very hungry. So I just want to let you guys know that I will do whatever I can. If you bring a problem to me, I will always try to solve it, unless it seems to be a somewhat unreasonable request that's maybe not considerate of the overall kind of course development. One person said that they wish the course was harder. To you, thank you. I'm glad that you find it very easy, but a lot of the class isn't. So we're going to keep the difficulty level at right here. If you are that person and want to reach out to me, I can try to find something that maybe pushes the boundaries for you, and I'm more than happy to make things more difficult for you if you would like. Just let me know and we can come up with something, or I'll try to find things for you. So on to this course. Coming back to steel column design. Thank you for that. I kind of needed it. That was weighing on my mind. All right. There's one other deviation I want to talk about. I got a message that you guys were feeling a little bit overwhelmed, so I did create kind of a summary outline of what we're doing, or essentially why we're doing it. It's more or less a summary of the first lecture of each term, but it maybe writes out some of the steps and some of the equations. Obviously, it's not all the equations. You have to be able to go look those up some yourself, but it does give an outline of where you might go look up an equation for example. So today, we're going to start moving on. We've basically learned all the theory that we're going to learn. Now we're going to start executing that theory by applying it to specific materials. So this is our first material class, where we're going to talk about steel. We're going to do each material over 2 courses, I believe. We might do concrete in 1. I can't remember what my layout is, but we're definitely doing steel over 2 lectures. Today, we're going to introduce the concept of steel columns. I'm going to get out my handy foam block to use as our column description. So before we dig into that, we're just going to have a quick recap about axial and bending, stress and strain. I might only even recap axial, we'll see. But today we're going to be focusing on the axial part anyway. So axial means, remember, compression or tension, so columns or braces. And then since we're talking about a material, we should know what we have available for that material, what it looks like, what are we using, how is it made, and what properties we know about that material. And then we'll dig in to actual brace and column design. So to talk about column and brace design, we have to talk about tension resistance, which is our braces. Oh, I forgot to change my mouse for you guys. Here, hold on. Let me bring up my mouse settings. You guys can't see it, but I am doing something. Okay, so I've made my mouse ridiculously large. There's only 2 settings for you guys. Tension resistance we'll use for braces, and compression resistance we'll use for columns. Now, tension's pretty easy. We pull on it, and it's just like that. Columns, if they're nice and short, no problem. But what happens when our columns are slender relative to their length? When we push on them, they try to buckle. Now, one of the questions I got was talking about the XX and the YY axes. And that's going to be really important. When we were talking about bending, look at this. If I'm bending like this, I'm bending about this plane right here. I'm trying to bend it like that. This is my XX axis. So anything when I'm talking about strength for bending, it's going to be the thing about the XX axis. But look at this. When I squish this, or if I did it like this, it's trying to bend in that direction. Or it's like there's a moment about that axis. That is our YY axis. And that's going to be important because we're going to use it when we talk about buckling. And buckling is going to be a really important part of our compression resistance. And then we're going to wrap up with 2 examples because I'm going to admit the final compressive resistance equation looks very overwhelming. It's scary, but if you break it down, and this is where I always like to write out everything I know and everything I don't know, and then go back and start figuring out all the things I don't know, and then maybe, oh, all of a sudden, I have all of the things I need to complete that very complicated equation. So we're going to work through 2 equations, or 2 examples that we go through a very full, long method. And the same way we did when we looked at different beam loading diagrams and deriving different equations, I'm going to have to make you do the complicated version of the equation, but I'm also going to show you an easy way to look up some of these values. Now, don't roll your eyes at me and say, Shannon, why do we have to do the complicated way if we can look it up in a table? It's because part of the mandate of the course is to teach you that. It is mandated, I have to teach you that, and we have to do it. But I will also show you the table way. Here's the advantage. If you know you have to do it out the long way, but you know there is a table, you could look up what your answer should be before you do the long, complicated equation. And maybe you'll at least be in the range of your answer. You'll at least know, oh, I'm pretty darn close to my answer here. So, and then there will be questions where you can just look it up on the table. It's not always going to be the big, long, complicated equation, especially where most of what we do is on Quercus now, which is, let's face it, sucks for some of this stuff. Normally it would have been a worked out math problem that you have to solve. I've toyed with you having to do it on paper and submit it, but I think it's almost better that we can use this as a way to phase out the complicated math equation where it was a very kind of linear step. I felt that there wasn't a great amount of learning on that in the final exam question. So this allows me to break it down into smaller steps that don't rely on the bits before, where maybe you'll learn it a little bit easier. So I think there's a real advantage here. Okay, so 2 weeks ago, we talked about axial stress and strain. We knew that stress equaled force divided by area. Strain, which is this weird unitless number, is our change in length divided by our length. So remember, axial is squashing and stretching. So squashing and stretching our object. And modulus of elasticity is the relationship between our stress and our strain, or E equals stress divided by strain, and it's the slope of our line in that beautiful elastic portion of our stress-strain curve. Now, if you combine these, you can rearrange them for any of these things here. All 4 of these equations are just the combination of these 3 equations, substituting things in. That's it. So these 4 equations are really just rewriting these 3 equations and combining them. So we have these at our fingertips. Look at this. If we were worried about the deflection or the change in length of a column, we would know that we would need to find out what force was on it. We would need to know how long it was before we applied load to it. We would need to know E, but we know that that comes from the material. That's something that gets tested on each material, and somebody tells us, oh, your E will be this. And A is a shape property that if we're checking to see what member works, we're picking the member we want to check, or somebody's telling us what member to check, so we can figure out what the area is. Same here with stress. We want to know the force. Last term, we knew we could figure out what the force on a column is. We find the tributary area. We find the loads that are acting on the floor from our load tables for dead loads and live loads. We factor those loads. So if we were talking about a dead and a live load, it would be 1.25 times our dead load times 1.5 times our live load times that tributary area that's loading up the column, and we've got our force that's being applied on it. And if we're picking what member we want to check, we're talking about the cross-sectional area of that member. So if this was our column that we're talking about, our cross-sectional area is this right here, or this surface. And the stress that that object sees is that force divided by that area. And if we know that different materials have a different limit on the maximum amount of stress we can see, well, we should be able to say steel, had a maximum stress of 350 MPa. And we knew our force and we knew our area, and the stress that that object was going to see was 349. Don't worry about reduction in factors right now. Well, 349 is less than 350. Our member should work. If we calculated our force divided by our area and we got 351, the stress that thing would actually see is greater than the maximum stress we let it have, which was 350. So we would start to fail. Now, if it's steel, that means we start to yield and we get large-scale plastic deformation. So steel is kind of a unique material that way. But a lot of materials, that's a hard limit, and we would have failure at that point. So that's what we've learned to date. That's what we know right now. So let's start talking about the material steel. Now, before we can talk about material properties, we should know a little bit about where steel comes from and what it looks like and how it's made. Now, there's two ways of making steel. We can hot roll steel or cold roll steel. Hot roll steel, now first off, all steel is cast. At some point, we take ore and we melt it down and we pour it into some shape. What we do with it after that point is determining whether it's hot rolled or cold rolled. So, large complex shapes are hot rolled. They start out basically in long sections that look like this. And we heat it up to red hot. We don't melt it, but you guys have heard me say before that heat lowers the capacity of steel, or it makes it less strong. So once it's heated up, we can make it more malleable. We can then roll it into the shape we want. And so what they do is they take this with maybe a roller here and a roller here and a roller here and a roller here, and they push it through the rollers, and it starts to deform. And then they move the rollers a little bit more, and then they push it through again. And then they move the rollers a little bit more and push it through again. And each set of rollers can eventually make a different set of beams. And we're going to see why that's important in just a minute. So we take red hot billets of steel and specifically formed rollers until the required shape is drawn out. Now, they usually have tight corners where we're at the edges of the original material, and where we've rolled it, we end up with soft, rounded corners. It usually is a black surface steel. Sometimes you'll hear it called black steel. And it usually, when it shows up on site, it rusts a little bit and it can end up looking somewhat brown. And if you touch it, it'll come off on your clothes just a little bit. So usually it's not very good in an exposed situation. We'd want to do something to it if it's going to be architecturally exposed. Cold rolled steel is usually sheets of metal, of steel pieces that are pressed or rolled into shape. And sometimes then we need to weld them to keep them into shape. So these are ones where the deformations that we're making in it don't limit its capacity too much. So examples would be metal deck, for example, and then our HSS sections, which literally start out as a sheet of steel, and we roll them into shape, and where the two seams meet, they weld them. Cold rolled steel is usually bright silver, not galvanized, which is almost a whitish powdery thing because of the zinc coating on it. And for those who don't know, galvanizing is what we'll do to steel. One of the things we can do to steel that's outside to help prevent it from rusting. But cold rolled steel will just look nice and shiny. It looks pretty good on site. It can sometimes even be used as the finished surface. So here are just some images of that hot rolling I'm talking about. So here you can see the rollers rolling it out. Now, the reason I said that there's a set of rollers for different groups of steel sections is important. Remember last term we talked about W150s, and W200s, and W250s, and W360s, but they had a whole bunch of different sections within that category. Well, you can imagine that all the W360s are rolled out on this roller, but as you squish that steel in it a little bit, it changes its proportions just slightly. So you might want to think about it as a grouping of steel sections because they're used on the same hot roller, essentially. I tried really hard to find a good video or even pictures of the hot rolling process, but it's something I think you have to see in real life because it's so bright compared to the background that it's almost impossible to get a good video or shot of it because it's so bright, it overexposes and the rest is hard to see. Here is a good example of cold formed steel. You can see that it's bright and shiny here, and this is kind of a siding or a facade piece of steel being cold formed. So our types of sections become pretty important. Most of what we're going to do is going to be with W sections or with HSS sections. W sections are I-beams, and I think I mentioned this last term, that it's really annoying that our I-beams are W sections because they don't look anything like a W. But the sections that were called I-beams were an old style of fabrication, and these were the newfangled new members in the industry way back when, probably in the 20s or 30s of the last century. That tells you that I'm old, that I have to differentiate that now. They needed a new name for them. They were the wide flanged sections. Eventually that old style of making steel beams disappeared, and now it seems kind of weird that we wouldn't just call these the I-beams, but that's the name they've got, and that's the name they're keeping, apparently. Now, the naming convention. So say, for example, we have a W150 by 30. That is telling us that it is around 150 millimeters deep, and it's pretty close to 30 kilograms per meter in weight, meaning every 1 meter of that beam weighs 30 kilograms. Now, if you look at the steel beam sections, some of them list a nominal weight and a theoretical weight. I had to pick one to go with for the assignment, so we picked theoretical weight. And so sometimes the theoretical weight has a decimal place, so it's very specific. Pay attention to that because, as we know, Quercus is very particular, and I tell you exactly how many digits to use, so pay attention to that in the question. If you're confused, sometimes that can lead you to the answer, but it very explicitly says to use, where applicable, the theoretical mass, because they'd be listed side by side. I'll say nominal mass or theoretical mass, and then some of them just have mass. That's it. So you'll have to pay attention to that and look and see. It'll be obvious as you go through those examples. Think of those as easy points, and I want them to be easy points. So remember, though, that it's only around 150 millimeters deep. To find out the actual depth, you can look in the steel beam tables, or the steel section tables, not beams, steel section tables, that will tell you D for the depth, B for the width, T is the flange thickness, and W is the web thickness. So these are our flanges, and this is our web here. B is our width, and D is our depth. And so remember, when we start talking about bending, we care about these two extreme fibers. They seemed very important to us, the top and bottom of those. Channels. We like to use channels for stair stringers, for small elements. They're not our main kind of beefy structural steel elements. They don't get called up very often, so we're not going to worry about them too much, but you can look up the properties the same way you can a W section. The naming convention is similar, where we have, for example, a C200 by 21. It's around 200 millimeters deep, but not exactly. You can look up D in the steel section properties. And it weighs pretty darn close to 21 kilograms per meter. And this is handy to write this in our name, is if we're trying to make a choice between two things when we're sizing it, if there's no other consideration, cost is going to trump it. I hate using that word. Cost is going to be what makes us decide what we use. Cheaper being better, obviously. We want to pay the least we have to. So if two things work, the one that costs less we might as well use. And you pay for steel based on how much it weighs. So you pay for the tonnage of steel. So if we have two members, if one is 30 kilograms per meter and one is 20 kilograms per meter, and they both meet all the other things we're going to learn, well then we'll take the cheaper one, no problem. And this lets us see at a glance which one is cheaper. The problem is we don't see our actual depth, our actual width, and then we would always look up our flange thickness and web thickness as well. Angles. Angles, similar to channels, we're not going to use much in this course, but the naming convention is slightly different than our channels and our W sections. L is for our angle, and then we have two dimensions. The first one is the long side, or what we'll call D. You could turn it on its side if you wanted to, and then we'd always write that it was long leg horizontal if we needed to do that. And B is our short side, and then 9.5 here is the actual thickness of our member here. Now, this gives us real dimensions, but it doesn't tell us anything about the weight. Now, often if we're talking about this scale stuff, they're so light compared to the rest of the structural steel that there's not a big cost implication with it. But if you're talking about two L102 by 76s, if you make this thicker, it's going to weigh more. So you can probably you can extract a little bit of information from that. I need to take a small drink. So hollow structural sections are cold rolled elements that start out flat and they roll them or bend them into shape, which means somewhere along here there's going to be a weld on it. Let's see if I can get this to work. So there might be a seam weld here, or a seam weld here, or a seam weld here on it. That can be important if you're talking about architecturally exposed structural steel, because it's visible. You can see that seam. If it's going in a wall, no big deal, who cares? But if it's going to be architecturally exposed, maybe as the architect you want to make sure you say that seam welds need to be hidden, for example. And so that's a whole realm of design in the specification about architecturally exposed structural steel. So the HSS naming convention is similar to the angle. It gives us actual dimensions. So if we have an HSS 152 by 102 by 64, we are saying that it is actually 152 millimeters deep and actually 102 millimeters wide, and the steel that makes it is 64 or 6.4 millimeters thick. So we have all of our actual dimensions but not our weight. So that's something we'd have to go look up in the steel sections property tables, which you have available to you. There are some other unusual sections. HP shapes are very heavy eye shapes. They're very stocky for their size, and they often use them for driving piles. So I think the name, actually, the P stands for piles. So when they're driving them into the ground. M shapes are very light eye shapes. I've never actually specified them. Super light beams, S shapes. I've never specified those three myself, but they exist and they're in the steel section properties. WT shapes, I'm leery about specifying. So they're a structural T shape. So what we're saying is that it's a shape that looks like that. But here's the thing, if you don't need a lot of it, it is literally a W section cut in half. So if you don't need much of it, you're paying for the full section just to use this part of it. Now, if you need all of it, no problem. You would use both sides of it in what you're doing, but it's not always an obvious choice, but sometimes it has good applications for it. It's not commonly used, but I just wanted to let you know that it exists. CFC and CFC are cold formed sections. Now, those would often be used as siding to help support cladding. So if we have, columns every 3 meters or something like that, these would span from column to column, and then the siding would span to it. They're usually very light, small sections, and they're not usually part of the main structural steel scope. And sometimes they actually even have another little lip on them there like that. So that would be the channel version or the C version. The Z version just takes the bottom part and flips it around. So we've got sometimes they're called Z girts or C girts. Now the one that is really fun and interesting is a welded wide flange. Now what happens if your loads are big and you don't have what you need available? It just doesn't exist. You can make a beam. I remember when I was at Blackwell and I was doing Solaris house, so for the owner of BlackBerry, Mike Lazaris, and they didn't have steel sections that existed, and no one in the company at the time had ever made up steel beams. They had some guidelines of some ones as recommended shapes. They used to almost pre-make them sometimes as well. Now it happens all the time, just because the scale of projects that we're seeing built in the industry is so much kind of grander, if you will. But a welded wide flange, sometimes they're called wide welded flanges. I do see that as I'm writing on this, the video camera's flicking a little bit, so I'll try to be very deliberate in my talking in case there's a funny little lag when it's happening. Ignore my not very straight lines, you get the idea. But they essentially take 3 sections of plate and weld them together. So you can imagine the cost involved in that you're actually welding up steel. Probably one of the most expensive things in a steel process is welding. You need certified, expensive people. They're the highest paid person in the steel shop, is the welders. And so we use these with great responsibility, essentially. They're not our first go-to. You use them when you have no other choice. So that's just our little recap about steel sections that are available. That's what we've got available to us in the world. Now you guys remember this diagram here, our full stress strain curve. Now for the most part, what we care about, let's find a good color here. What we care about is this zone right here and this line right here, where we say the max, that's an unfortunate image. What's happening here? Sorry about that. The mouse, or not the mouse, the USB plug for the camera is very sensitive, and as I was writing on my laptop screen, which is where the mouse is, which is where the camera USB is plugged into, it must have jostled it. That was a very unflattering freeze image of myself, and I'll just have to live with that. So we can see that in our stress strain curve, this is the range that we care about. Anywhere along here, we're typically happy with. And this is where we top it out. We might let our member yield all the way to the neutral axes and stop right there, but we're still stopping at this 350 MPa. Now, in a few minutes, I'm going to show you something where we do make use of that ultimate stress. I do see the funny lag happening. I will try to be very careful with it. I apologize. I'm working with the technology I have at hand, so I'll try to draw, let it catch up, and then talk. But there is going to be some small applications where we use stress ultimate, simply because steel can have some large-scale deformations. Now, we're going to see a very specific use of where we can use ultimate stress for steel, and I'll talk about why it's okay in that specific example. So here is some steel properties. You should know these. I do include them in the appendix for the exam, but you should know these. Fy is just another way of writing stress. Okay, yeah, you can see me. So Fy is just another way of writing the stress when it yields, or the maximum stress we want this thing to see. And for us, steel, that maximum stress we want it to see, is 350 MPa. Now here's a funny little clause, and because there's always exceptions to everything, you guys are all going to roll your eyes at me. I know, but I don't make these rules. This is how it is. HSSs are cold formed. Now, steel, before we manipulate it, the steel that we make is 350 MPa. Cold formed steel, great. We bend it into shape, we weld it up, we've got our 350 MPa steel. Our hot rolled sections, when we heat it up and we roll it back and forth through those rollers, there leaves some locked in stresses. And when it cools, those stay locked in. So we lose a little bit of capacity in our hot rolled steel. So remember, that's our channels and our angles and our W sections. So for us, W sections is a big deal because we're going to be doing a lot with W sections. So when I say Fy, you have to know if you're talking about an HSS or a W section, because if it's an HSS, you need to use 350 MPa. And if it's a W section, you need to use 345 MPa as your maximum stress you want to let your thing see. Stress, I can tell you, writing the Greek symbol all the time is a huge pain in the butt every time I'm typing something. And I am guessing that's why a long time ago in the industry they said, screw that, let's make it Fy, so that we don't have to keep writing this Greek symbol, finding the symbol chart or changing the font every time we want to write it. So Fy is just another way to talk about the maximum stress we want our steel to see. 345 MPa for W sections and 350 MPa for HSS sections. E of 200,000 MPa for steel, we already knew. We already talked about that. G I told you is related to E through the Poisson's ratio. Not an equation you need to know. We're not going to spend any time talking about it, but we are going to need it in our equations. I think it's enough for you to know that it is related to E, and that it has something to do with bulging when we squash things. That's enough. So I will give you this. I've already given it to you. G equals 77,000 MPa. Now, here is the thing we need to know. We have all this time been talking about MF needs to be less than MR. MF is, or let's see, since we're talking about axial loads, how about I write it as one of the axial components. CF needs to be less than CR to be strong enough. CR is our capacity. CF is the load that's actually on it. So we say, let's take the load that's actually on it and say maybe we got it wrong and it's actually bigger. And then let's take the capacity, or how much load it can withstand, and say, let's reduce it a little bit in case we got it wrong, and then make this reduced capacity be less than this factored load. Last term, we learned how to find the factored axial loads on an object. We looked at tributary area, we looked at the loads, we factored them, we then multiplied that factored load by the tributary area, and then we even drew pretty little diagrams of those elements just so we could easily illustrate what those loads looked like to ourselves. And then we would pull out, here's the maximum load we see. Well, now we're talking about this side, the capacity, or the CR. And so we're going to need to incorporate these reduction factors in some way. So this, if we've applied these reduction factors, it means we can use our CR. The same way that if we applied our load factors, we could start writing this little sub F. Don't worry, we're going to do an example at the end of this lecture that starts at the beginning of what we did last term and goes all the way through the end for a steel column. So most steel is 0.9 as a reduction factor. Rebar is 0.85, and that's going to come up when we do concrete. Bolts are 0.8, simply because, they have different manufacturing standards. Shear connectors, or elements that we use to connect our shear elements, use a factor of 0.8. And anchor rods, the things that go into the ground to hold our columns down, use 0.67. Do you guys remember last term when I said probably the number one thing that happens wrong on a project is that anchor rods get cast in the wrong spot? Well, that's just one of the wonderful reasons that we have this 0.67 in there. Okay. So now we're going to look at column, and I'm going to change that to say column and brace design. So on slide 12, column or brace. Axial loads. We're going to look at tension resistance, we're going to look at compression resistance, and we're going to look at compression squashing, buckling. We're going to talk about a few small things, and then we're going to bring up the big formula that's going to be very scary, but then you're going to breathe a sigh of relief because I'm going to show you some design tables. And that might make things a little bit easier. Before we do that, I just want to refresh you guys on something. Now, I had written something out for myself. I guess I don't have it anymore. So let's just think for a second what we already know about axial loads on a cross-section. We, earlier in this term, looked at this equation. Well, we know that this is stress, this is force, and this is area. So area covers our cross-section. That's our cross-sectional area. It's a shape property. P is our force, or that thing we calculated last term. P is a placeholder to talk about axial loads. We'll use P as a placeholder for C or T, or compression or tension, depending on what we're talking about. Let's rearrange this equation. Well, look at this. We've got P equals stress times area. Now, if we want to know what our capacity is of our element, remember, let's maybe sub this in. Let's talk about compression, or I'll write them both out for you. So that's saying compression or tension equals stress times area. We want to make sure we're talking about reduced capacity. We want to make sure we're looking at the maximum this could possibly take. So the maximum load this cross-sectional area could take is going to be the reduction factor times the maximum stress times our area, or our cross-sectional area of whatever member we're talking about. So we get to add our little r there because we've incorporated this reduction factor. Well, we know that if we're talking about steel, this stress max is our yield stress. So that's where on our stress strain curve, E is on that sloped part. That's just like that. When we get to that part, that is our Fy, or the maximum stress we want our object to see. So did it do it again? Okay, hold on. Let me turn this off and do it again. Sorry, I've even tried plugging it into a different spot, but the software won't recognize it if I plug it into the charger base. It'll only work if it's plugged into my actual screen, the thing that I'm writing on. So we'll go make it work. Sometimes I might freeze, and you'll see a little blip in the video. So we can see here, just by this is simply the thing we've already looked at. Stress equals force divided by area, which is something that you intuitively know. If you take a weight of something and spread it over an area, you can talk about stress. All we've done here is formalize this a little bit. We know that we can use a subscript r if we're using our reduction factor, because that's what we want to do. We want to find out the capacity of this member. Fy is the maximum stress we want our steel to see. We call it our yield stress. And A is a shape property that we get from the cross-section of the member we're talking about. One last thing. So one last thing. We want CF to be less than CR, or essentially we want our CF to be less than the reduced capacity of our maximum yield stress times the cross-sectional area of our member. And if that is greater than the applied load, yes, we've got a column that works. Except tension No problem. All of this works whether I use C or T. C meaning we're talking about squashing, and T meaning we're talking about pulling or tension. Tension, no problem. This equation is beautiful. It's perfection. We can say so TF needs to be less than our reduction factor times our maximum yield stress times our area. But compression isn't going to be that simple because of that. I'm sorry, tension's actually pretty easy, but we don't actually use tension that often for our structural elements. All of our building comes down on our columns. So this phenomena of buckling is going to be really, really important to us. So let's talk about tension resistance, or our tension capacity. Well, look at this right here. TR equals reduction factor times AG. G just means the gross cross-sectional area, or the actual cross-sectional area that you'd be used to talking about, times Fy. That's exactly what we wrote on the other page. They just, for whatever reason, like to mess with you and switched which spot A and Fy are in. Same thing, that is directly from stress equals force divided by area. We just, step by step, in a very easy way, got this equation. Now, in tension, we often have holes in things to connect them. And because we don't have buckling as an issue in tension, we often end up right at the limit of its capacity. Now, if what we're talking about is cross-sectional area, so if this is the thing in tension, this is the cross-sectional area, what if I cut a hole through this right here? I've got my tension on it, and the tension here is the same as the tension here, is the same as the tension here, which is the same as the tension here, which is right through where the circle goes through, or the bolt hole that's in my element. The cross-sectional area there is different. It's less. We've got less cross-sectional area. So, do we use that area? This is where they've done many studies, and they've determined, and in fact, they started out doing that. They said, okay, use the cross-sectional area where there's the least cross-sectional area, and that is going to be your capacity. So if we have holes through this, you don't use this cross-sectional area, you use the area right through where the hole is. But what they've determined is that if the hole is relatively small, or, within this element, that there is some ability for the stress to kind of go around it a little bit. Now remember, we have that ultimate stress, and this is where I said it's going to be the only time in steel that we talk about ultimate stress. There is a slight ability for steel to kind of flow the stresses around that hole. So what they've done is they've said there are two equations you need to think about, and the lowest one is the one you have to worry about, because you want to make sure that your load is less than these two things. So your load has to be less than both of these things. So we're still using our same material factor, but here we use the net area, or the area through our opening or our hole. But because of that ability for steel stress to kind of flow around it, we'll use our ultimate steel load. So remember, Fy was 350 for an HSS and 345 for a W section. Let's just go back and look here. Fu, though, was 450 MPa. So we get to use a little more capacity there. And we don't know just by looking at it which one governs. Remember, both of these have to be greater than the load on it. So both of those things have to be true. So whichever one of these is lower is going to be our upper bound, or the limit of load that we can put on this object. AG is the gross cross-sectional area, In any other formula, we're probably just going to write A, because we don't need the G, because we're not trying to explain that it's different than the net cross-sectional area. ANE is the net cross-sectional area reduced for bolt holes or things like that. So if we had that opening through here, it's the area that's left where we have that opening. Fy is the yield strength of the steel, or normally the limit of stress we ever want our steel to see. And Fu is the ultimate strength of our steel, the absolute maximum load this thing can take. We're not going to worry about pin connections in this course, but I just wanted you to see that there is actually even another formula when we're talking about pin design, but don't worry about that right now. So let's do an example where we look at an element making use of the gross area and where it has an opening through it. So we have a brace that is 100 millimeters wide by 200 millimeters deep with a 60 millimeter diameter pipe opening through it. We want to know what capacity does this brace have if the steel is 300 MPa steel. So it's not our normal steel. It's not our 350 or 345 MPa steel. Interesting fact, when I started in the industry, many of our materials, including plate and channels and angles, were made with 300 MPa steel. The steel code has said we don't have to accept that anymore, that we can say it all must be 350 MPa steel, or 345 if we're talking about hot rolled sections. But every now and then this 300 MPa steel still shows up on projects and sites. So a lot of engineers will still design plate as 300 MPa steel, mostly out of habit because they know that if they design it as 350, they'll get a call. Don't worry, unless I tell you otherwise, you're doing 350 or 345 MPa. But you've been told otherwise in this example that it is 300 MPa steel. So let's figure out what we know. So we have a brace. Why don't I make this bigger for you? We have a brace in tension. I'm going to add that to that note as well. So I'll clarify that in the question, that it's under tensile loads. So what we know. What we know. Well, we have some stuff we know about the steel. The steel we know is 300 MPa steel, or steel that has an Fy of 300 MPa. We know that steel, all of the steel we use, has 200,000 MPa modulus of elasticity. We know that E is 200,000 MPa. We know that for all of our steel. We also know that it didn't matter what the steel grade was. Fu is 450 MPa. And we know also for steel that the reduction factor is 0.9. Let's draw ourselves a little diagram. I don't normally do this for this question, but I'm going to, just because. We've got a brace like this with a tensile force on it, meaning there must be an equal and opposite tensile reaction. So there we've got a little free body diagram that we've drawn. And we know that our member looks something like this. I'm just cutting it off there. And somewhere in it, there's a hole in that pipe. So let's write what we know about the member. We know that D is 200 millimeters. We know that B is 100 millimeters. They gave us that in the description, in the question. They said that it was 200 by 100. We don't really care what we call D and B. It doesn't really matter. But we tend to often call the deeper dimension D. So we're just going to stick with that for a minute. And they've also told us that the hole diameter was 60 millimeters. Now, don't get confused. This is also the symbol for diameter. Why don't I write diameter just to not confuse you? Because reduction factor uses that same symbol. We want TR. Now we know that the equation for TR, there's two of them. The reduction factor times the maximum yield stress times the gross area, and TR equals 0.85 times the reduction factor times our net area times FU. Well, let's figure out the gross area. We already know our reduction factor, it's 0.9. We already know Fy is 300 MPa. Gross area is the next thing we don't know. Well, gross area is that area right there, or 200 times 100, or 20,000 millimeters squared. We also need, so that gives us everything for that equation. TR is what we're looking for. 0.85 is easy. The reduction factor is 0.9. We know FU, so it seems like the only other thing we need to figure out is the net area. Now the net area is where we have the least amount of area. So that's going to be right through here. Now look, if we did it right here, if we made that cut right here, we've got our full area. If we drop down a little bit, we've got a little bit less area, and down a little bit more, but it looks like the maximum hole size, or the most material removed, is going to happen right where we go right across the widest part of the circle. So essentially, if this was our cross-sectional area before, where that's 200 and that's 100, I haven't drawn it to scale very well, and that's 60, that is the cross-sectional area that we're left with right there at that point. So our net area is our 200 times 100, but minus this amount right here, or 60 times 100. So that'll give us that little bit that's left. 200 times 100 minus 60 times 100. Or we're left with 14,000 millimeters squared. Now it looks like we have all the information to calculate our TRs. So TR might be 0.9 times 300 MPa times 20,000 millimeters squared. 0.9 times 300 times 20,000 gives us 5,400,000 newtons. So this is where I always tell you, as much as this gives us in newtons, and it needs to because we've been working in MPa and millimeters squared, once we get to TR, we kind of like to talk about it in kilonewtons, which means we divide it by 1,000. So 5,400 kilonewtons. But there's two equations we need to check. The other one is our 0.85 times our reduction factor times our net area times our FU. So 0.85 times 0.9 times our times our 14,000 times our 450 MPa so we have 0.85 times 0.9 times 14,000 times 450, we get 4,819,500 newtons, or 4,819.5 kilonewtons. Well, both of these are TR of our element, but we want to make sure we don't overload this. This is the maximum load our brace can see. They're both calculated. The lower one is the maximum our brace can see. If we said that these are both the maximum force our brace can see, and we have 4,000 kilonewtons on it, it works no problem. If we have 5,000 kilonewtons on it, it works for this equation, but not this equation, and it would fail. So TR for this brace is 4,819.5 kilonewtons. Now, I always like to put a big fancy box around things so somebody can take a look at this and go through it if they need to, but there's your final answer in big, bold information. Now, the reason we have to do both equations is because it's not obvious which one is going to govern. If this had been a very small diameter hole, what if it was only 10 millimeters? Let's just plug this in. 200 times 100 minus 10 times 100 is 19,000. Let's try 0.85 times 0.9 times 19,000 times 450. We would have gotten a capacity of 6,540. So then the overall gross area equation would have governed. So you still have to check both because it's not, you don't know which one is going to govern. It depends on the size of that hole or that opening relative to the gross area. So let's move on to compression. Now, in theory, the basis of the equation is the exact same. Remember, our stress equals our force divided by our area. We rearrange it. The yield, the force that it would yield at, is equal to the stress it would yield at times the area. Now, don't get confused. I only put the sub y to say that this is the force it would yield at. I'm just trying to illustrate that we're talking about that yield stress. So if this is our yield stress, if that's the stress it'll yield at, that's the force it'll yield at. Once we apply that reduction factor, we're going to put a little sub r there. Don't worry. Now this is still only about strength. And if it's just about strength, that's fine. Look at this. If I keep this nice and short, When I squish it, it's just fine. But if I try to do that with a taller object or a smaller cross-sectional area relative to the height, it tries to buckle. This equation is just about strength. We need to do something that takes that buckling into account because it seems to be pretty important in the axial component of this equation. Now, this is where it looks terrifying. Don't worry, we're going to walk through this slowly. It's not as intimidating as it looks. The hardest part about this equation is using your calculator well. So, P critical is the critical load or the buckling load for your element at that length. So, if this element is this long, I want to know at what load does it buckle. So when does that happen? What load do I need to apply? Because look, it doesn't seem to happen with a little bit of load and then all of a sudden it buckles. So that seems like a very critical load. And so the critical load or the buckling load is this equation here. Now look, we have pi, that's easy. EI. Well, E, we know, is all about the stiffness of our material, and for steel, it's 200,000 MPa. So we know both of these two things. I. Now this is where I said knowing what direction your thing is moving is important. Last week, when we were talking about bending, we were talking about things bending about this axis, like this. So that was our x-axis. So we were worried about s-x-x. I know, that sounds very funny. S-x-x. When we're talking about buckling, look what direction it tries to buckle. It tries to buckle in its weak direction. Or it looks as if it was bending in this direction, or about our y-axis. So that's why, for this equation, we are usually going to be looking at I, Y, Y. So the moment of inertia in the direction that the member is allowed to buckle. Now, here's the interesting thing about buckling. Normally, I, live in the class, get someone to come up and put their finger right here. And when I try to put this load on it, look, you can see how much more I'm squashing it, and it's not buckling. So halfway point, I've just stopped this from buckling, and I get people to tell me, did it feel like much force? And they're always very surprised by how little restraint it took there to stop it from buckling. If you guys remember our multi-story columns, we had braces or we had pins at the loads because it was held in place by the floors there. Well, we could put a brace somewhere else on that member if we wanted. So we have to be smart about where or what direction it's trying to buckle. For our steel columns, it's often going to be about the YY axis or in that weak direction. You know, you can imagine that that's the weak direction. Now, down here they have KL. It's a small k. L is pretty obvious. That's the length. For everything we do, our KL is going to be actually L. So this K will be 1 for everything we do, except for a visual graphic you do in the assignment. But it is a visual based on this right here. So these are effective lengths of columns. Basically, what it's saying is, if we apply restraints, different restraints at the end of elements, it holds it in place a little bit and changes the effective length of the element. Remember, you are always going to be doing this one right here, where it's 1. I'm not going to make you do anything else but this one right here. But look at these other shape restraints. What we're saying is, instead of, see my hands here, it's allowed to rotate top and bottom. But if I don't allow this to rotate, if I hold it in place, essentially a moment connection, look at that shape, look at that pink line. It looks like this element here. Well, remember, that is the symbol, or that is the diagrammatic way we represent a moment connection for a support. So essentially what they're saying is that it's only trying to buckle over a much shorter length if we change our end supports. Now again, you're just going to be doing a pinned one, but it's important to know that that end restraint is important. Now, probably thinking, well, if it shortens our effective length, why don't we do it all the time? Because it comes at a premium. If we've got moment connections here, all of a sudden we have to weld them up and make the moment connections and design them. And last term you guys saw a lecture on the impact of moment connecting all of our things together. That it can work and there can be advantages to it, but we have more material, we have more deflection of overall shapes if we're talking about our lateral load resisting system. So it's still not a thing we do lightly, but if we've done it, we might as well take advantage of it and reduce that effective length. So here's the interesting thing about compression buckling. There is no stress element in this equation. There is nothing to do with stress when we're talking about buckling. There is the load it will buckle at, but we're not talking about strength. We're dependent on the weak axis stiffness. That's what we're talking about, is how stiff is it in the weak axes. So if we said that P squashing is just our normal axial load equation, or force equals stress times area, and this blue equation, or this blue line, is that critical buckling load, it makes sense that P squashing doesn't change. There was nothing about length in P squashing. Let's see how well this works. Oops. So P squashing is our force times our area. There's nothing about length in there. So if you change the length, this P stays the same. There's no difference. Doesn't matter how short you are or how tall you are. P stays the same. P critical, or the load that your element would buckle at, as it's really, you can imagine as this gets longer and longer and longer, it would take much less load to make it buckle. So this is a plot of the critical buckling load. And as the thing gets really tall, it buckles very easily, or at a very low load. When it's really, 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 really short, the critical buckling load is off the chart. It's almost infinite. It could not buckle. So if it's short, it looks like P squashing governs it, because that's a limit. That's the maximum load it can take. And as it gets taller, buckling seems to be the limit on the object. So it makes sense that our final compressive resistance of our element is some combination of P squashing and P critical due to buckling. If our column is very short, it's almost exclusively due to P squashing, or the equation we know and love. As it gets taller and taller and taller, it gets very easy to buckle sideways, and it tends to take over the design. So this red line, CR, is the final compressive resistance equation of a steel column. I'll show it to you on the next slide. I do want to note this point right here. At a certain point, we say, this thing is so tall and the load is so effectively close to zero for its height that we don't care. You're just not allowed to build that high. If there's any small variance there, that thing is going to buckle. So we put an actual upper bound limit on that element in compression. So here it is. There's your compression equation right here. CR equals reduction factor times area times Fy. Well, that's pretty easy. That is our normal compressive resistance equation. And then we have this portion right here. 1 plus lambda to the power of 2n, and then that to the power of -1 divided by n. I know, it's a crappy equation. It's very intimidating, but let's just stop and break it down. Reduction factor, we know, is 0.9 for steel. I've already given you that. A is just the cross-sectional area of our element. No problem. We're looking at our element. We're picking our element, and we know what cross-sectional area it has. Fy is the yield strength for steel. So 350 MPa if we're talking about an HSS, and 345 if we're talking about a W section. Lambda. They've given us a breakdown for lambda here, and they've written it 2 different ways. What they're really doing is rewriting that critical buckling equation. So this is just a reworking. You can see they've still got the KL, and they've got the pi squared and the E. So this is just a reworking of that buckling equation. You don't need to worry about it too much. And look, I is missing. We're not using I anymore, which seems weird because I just showed you that I was really important. Well, this is where I'm going to tell you that we have another shape property. Yes, I know, another shape property. And this R here, this lowercase r, is bound to I. So it is related to I. You don't need to worry about it. It's beyond the scope of this course, but we do need to be able to look it up. And you're going to be able to look that up where we look up all the other section properties. And really, this is talking about it's another way of talking about extreme fibers. If you guys remember that I was all about extreme fibers. And so this is just another way of talking about that. So this FCR is just a rewriting of that equation. We're going to stick with doing it this way, I think. So lambda will calculate this way. So KL, well, that's the length times 1, because we're only going to be doing the equation using a KL or a K of 1. R, I've told you can look up. That's no problem. We can look that up in the steel section properties. Square root of, well, Fy, we know, that's the yield strength of the steel. So that's no problem. Pi is a constant, and E is our 200,000 MPa. That's our modulus of stiffness, or our Young's modulus for steel. And then N I'm going to give you as a constant. For other types of shapes and other types of things, it can be a variable, but most of the time N is 1.34. So don't worry about that too much. You just need to know that N is 1.34. And then here I said R is radius of gyration. That's a typo. Why don't I fix that as well? Radius of gyration. It's, again, I said, another shape or section property. Same as A, S, Z, and I. It's just another shape property. In fact, when I talked about shape properties 2 weeks ago, I showed you that R was on that same list. But look, CR equals 0 if KL divided by R is greater than 200. That is this limit right here. So CR equals 0 as soon as our length divided by R is greater than 200. That's a limit. We don't let it go greater than that. So that's the upper bound on our equation. Do we have to calculate that every single time? We have to do it a couple times because that is the mandate of the structures curriculum via accreditation. So we're going to have to do it a little bit, and I'm going to do 2 examples for you at the end of this lecture. But, like you've seen with most things that are really hard so far, if we're doing it, it means somebody else has probably done it, which means they've probably made a table of it. So, let's take a look at a column design table. I have uploaded for you, and it's in the uploads or downloads module, but also in this week's lecture module, the steel column tables. So in this, you will see different CRs that have been calculated based on the length of the column. So let's look up the capacity of an HSS 127 by 4.8 that is 3.97 millimeters, or 3,975 millimeters long or tall. Well, I'm gonna pull up this. Well, here we have, sorry, it changes to this fuzzy, funny hands. Oh, you know what? I can make it. There we are. So we're talking about 350 W steel. Don't worry about Class C. And look, they've incorporated the reduction factor of 0.9. So they've already done that for us. We were talking about an HSS 127 by 4.8. That is 3,975 millimeters long. So let's go back to that table. A 127 by 4.8. Oh, it looks great. We've got a chart here with different CR capacities, or resistance, factored axial compressive resistance, CR, in kilonewtons. They said we have a height of 3,975. Well, look, here they have KL in millimeters with respect to the radius of gyration. Well, KL, I've told you can use a K of 1, so 1 times our 3,975. We're going to stay with 3,975. So it seems like we are going to have a compressive resistance somewhere in between these two, but closer to 4,000 would be my guess, or the value for 4,000. So let's come over and take a look at these. So if it was 4 meters long, our compressive resistance is 272. If our column is 3.6 meters tall, our compressive resistance is 309 kilonewtons. So we should be somewhere close to 272, but a little bit more. Because look, as it gets shorter, we have more capacity. So we're a little bit shorter than 4 meters. But we should be pretty darn close to 272. So you can see here that I've highlighted that column, and highlighted there. So if the length was 3,600 millimeters, CR is 309. If it's 4 meters, the CR is 272. But we want to know CR at 3,975. This is where we interpolate. So we interpolate here. I've gone through interpolation a few times. You can try plugging this into your calculator. You can try doing it by hand if you like. But we calculate that CR is 274.3 kilonewtons if our length is 3.975 meters. Well, this makes sense. We're just a little bit greater than our 272. Seems like a reasonable number there. So we have a capacity. If we had a column that had 305 kilonewtons on it, doesn't look like our element works. We either need to find a bigger member or lower our story height, make our column shorter. That seems a bit weird. So we'd probably go with a bigger element. So I said 305. Let's, just because I'm feeling like it, let's see what happens if I bring this up. I have to switch back and forth between my screens. So, so close to 4 meters. Oh, look at this. An HSS 127 by 6.4 at 4 meters tall has a capacity of 351. Our 3.975 meters, we should have a capacity just a little bit greater than that. It looks like if we had a factored load on it of 305, we'd be okay. But we can say that our HSS 127 by 4.8, that is 3.975 meters tall, has a capacity of 274.3 kilonewtons. So let's start doing some examples now. We'll go through 2 worked out full examples and we'll cross-reference it with the tables. So we've been asked to design a steel canopy for an existing building. So it's a building that's already there and it's in Brampton. The height of the canopy is 4 meters and it's matching the top of the existing building. So it's not lower than it, which means it seems like we don't have to worry about accumulated snow loads, which remember that was a thing we talked about last term. The snow load requirements for Brampton is SS equals 1.3 kPa and SR equals 0.4 kPa. They've said that the roofing assembly for this canopy is going to be 4-ply roofing with gravel, 38.9091 steel deck, 12 millimeters of gypsum wallboard soffit, and they've told us to allow 0.24 kPa weight allowance for structural steel. Now I'm going to tell you that this is a really bad design because nobody wants to put gypsum wallboard soffit out in a real project outside because the underside of this canopy is going to be exposed. But we might give that feedback to the architect and they can do with it what they want. Now, the architect wants to know if an HSS 64 by 64 by 3.2 using our normal 350 MPa steel works. They say we've been asked to look at the steel selection tables and then we want to verify it using basic principles. So everything we've just done. And then they also want to know, they have some questions, they haven't decided fully on their design intent. So they said, what about a W150 by 30 as well? Could we maybe take a look at that and see if that works? So we have 2 different members we need to check, an HSS and a W section. Remember, the W section would have 345 MPa steel instead. So before we can do anything, we have to figure out what the load on this column is. To see if it works, we need to know what the load is as well as what its capacity is. So let's talk about our steel column example. We need CF to be less than CR. So that means we need to calculate CF and we need to calculate CR. So the CF we learned last term. That's what we learned in Structures 1. So let's start looking at CF. This is what we learned last term in ARC2044. So we know that we need the loads on this. Well, we have dead loads. The dead load, they gave us a few different elements that make up the roof, and we need to figure out what that dead load assembly is. They said there was 4-ply with gravel. They said there was 38 deck. They did tell us that it was 0.91 millimeters thick. 12 millimeters of gypsum wallboard soffit. And they gave us an allowance for steel. That one they gave us is 0.24 kPa. Let's look at our dead load tables. So this was something that we looked at last term. We looked at these tables here. And the first thing we want to look at is 4-ply with gravel. So 4-ply asphalt with gravel is 0.32 kPa. The next thing was 38 millimeter deck. Well, steel decks, 38 millimeters deep, up to this thickness, is 0.1 kPa. And then they gave us 12 millimeters of gypsum wallboard soffit. So let's take a look. There's plywood, there's chipboard, gypsum wallboard. So GWB is gypsum wallboard per 10 millimeters is 0.08, but we have 12 millimeters of it. So 12 divided by 10 times 0.08, we've got 0.096 kPa of gypsum wallboard. We can add up the total weight of our roof assembly. So 0.32, oh my goodness, 0.32 plus 0.1 plus 0.96 plus 0.24, we have a roof assembly of 0.76 kPa. So I rounded just a little bit there. It was, if you work it out, it's 0.756, but I rounded it up. The other thing we need is the snow load. They gave us that SS equals 1.3 kPa and SR equals 0.4 kPa. We know that the snow load equation equals the importance factor times SS, and then SS is multiplied by our basic ground snow load, our slope, our wind, and our accumulation factors. And then we add SR. But we also know we need to be tracking that serviceability load. I've told you guys that we should be tracking that as well. And that is everything the same except for we're going to use the serviceability importance factor. So our serviceability, or our importance factor, is 1 for factored loads and 0.9 for our serviceability load cases. It's a normal building. There's no reason to think otherwise. CB is always 0.8. CS is about the slope. They haven't said anything about it being sloped, so if it's flat, it's 1. Our wind factor, there's no reason to think we could possibly reduce this. I said that it's almost impossible to be able to reduce the factor for wind by exposure. So this is saying that if it's out in the open, the wind can blow the snow off, but you have to have nothing taller than it for a kilometer away from it, which is almost impossible in our zone here. Certainly in Brampton. Maybe in the prairies, you could get that. And then north of the tree line, they have another equation for it as well. And then we have our snow accumulation factor, or our accumulated snow load factor. We have a flat roof beside another flat roof at the same height. So there's no snow coming off and falling on that lower roof. So we don't have an accumulated snow load factor. I also told you guys I wouldn't give you any problems that had an accumulated snow load factor. So it looks like we can calculate our snow loads. So our ultimate limit state snow load calculation is 1 times our 1.3 times 0.8 times 1 times 1 times 1 plus 0.4. Let's plug that into our calculator. 1.3 times 0.8 times 1 times 1 times 1 plus 0.4 times 1 equals 1.44 kPa. Let's track our serviceability snow load at the same time. We have 0.9 times the bracket times 1.3 times 0.8 times 1 times 1 times 1 plus 0.4. Look. It's the exact same equation, except the only difference is instead of being multiplied by 1, it's multiplied by 0.9. 1.44 times 0.9. 1.30 kPa. So we have our dead load and we have our snow load. Now we can think about factoring our load. We can factor our load now. We have a few different load combinations we need to worry about. Our 1.4 times dead load, ultimate dead snow. We don't have a live load, so we're not going to worry about it. We could go through it if we wanted to. So I'm just going to calculate this out. So our ultimate dead and snow load case is 1.25 dead plus 1.5 times our snow load. So we've got 1.4 times 1.4 times our 0.76. So 1.4 times 0.76 equals 1.06 kPa. And we've got a load case of 1.25 times 0.76 plus 1.5 times our snow load of 1.44. 1.25 times 0.76 plus 1.5 times 1.44 equals 3.11 kPa. So it looks like that's the maximum load that this is going to see. So we're going to need to keep that. We should also be tracking our serviceability load cases. So we have serviceability, dead and snow, and serviceability snow all by itself. Now we're talking about columns here which don't really have an allowable deflection or a maximum deflection we're worried about. But it's always a good idea to track this stuff just in case. You never know when you might need it. So our serviceability load cases is 1 times dead plus 1 times our snow load and 1 times our snow load. So 0.76 plus 1.44 and 1.44. So 0.76 plus 1.44 equals 2.20. Ugh, my goodness. Does anyone see what I did wrong? I'm not using 1.44. We're talking about serviceability. I need to use 1.3. So we're talking about 0.76 plus 1.3 or 2.06 kPa and 1.3 kPa. So we've tracked that information, but what we really want to know is what the load on that column is. Oops. So here we have our diagram, there's the existing building back there, and here's our canopy. We want to know what the load is on one of these columns. So the tributary area, if this was a table, you guys would intuitively know that if I spread a load all over this, a quarter of it is going to go here, a quarter of it's going to go here, and depending on how the support was, if there was columns here, a quarter would go to each of those. It looks like the framing might mean that means that there's actually a uniformly distributed line load on this element back here. But we understand that these are each taking a quarter of the load. So our tributary area, so let's look at the load on the column. Our tributary area equals 6 meters divided by 2 times 5 meters divided by 2. 6 divided by 2 times 5 divided by 2 is 7.5 meters squared. So the CF on our column is our tributary area times our load, or 3.11 kPa times 7.5 meters squared. Remember, kPa is kilonewtons per meter squared times meters squared. We are going to get 3.11 times 7.5, 23.3 kilonewtons. So we have one side of our equation. If we come up here, we now have CF. But now we need to figure out what CR is, because we need CF to be less than CR. But they've given us a specific column they want us to check. We want to check CR of an HSS 64 by 64 by 3.2. Now, we know that there's a big, ugly, nasty equation of CR equals our reduction factor times our area times Fy times, in brackets, 1 plus lambda to the power of 2n, end our brackets, but that is to the power of minus 1 divided by n. So let's write out what we know. Let's write out what we know about the steel. We know that the reduction factor is 0.9. That one's kind of easy. We know that the Fy is 350 MPa. They told us that in the equation, but without any other information. An HSS in today's design world, we would use 350 MPa. And we know that steel has an E of 200,000 MPa. Maybe we need all this, maybe we don't, but it's good to write out the things we know. Let's write out what we know about our member. That is an HSS 64 by 64 by 3.2. Well, this is where it might be handy to look up our beam selection tables. Not our beam, don't mind me. Our section properties. I should open that up, and I did not. Give me but a moment. Steel sections, here we go. All right, we want to find HSS 64 by 64. Oh, look at this. All right, HSS 64 by 64 by 3.2. We have all kinds of properties here. We can look up all kinds of different things. Look, there's only one type of I, S, R, and Z. They don't have it in two different directions because this square HSS is symmetrical. Things are going to be the same in each direction. So let's bring our highlighter down here. 64 by 64 by 3.2. Because my mouse is an awkward size, it's not letting me highlight things quite the way I would hope. There we are. There we go. We have all kinds of properties we can look up for this particular section. We have an area of 741. Oh, look, here's that R, that weird R we've talked about. 24.4 millimeters. And I, let's take a look, I. We have 0.441 times 10 to the 6 millimeters to the 4. Now, you don't always know everything you need to pull out. Don't worry about it. Pull out the things you think you might need. You can come back and look up the rest if you need to. So we looked up that the area, the cross-sectional area of that column was 741 millimeters squared. We looked up R, and it was 24.4 millimeters. I, or our moment of inertia, was 0.441 times 10 to the 6 millimeters to the 4. Yeah, crazy number, I know. Now, length. They told us in the question that this canopy was 4 meters tall. So, it looks like our length is 4 meters, and K is 1. Because I've told you that all the columns we're going to do are going to have an effective length factor of 1. And then there are a few other weird things that we can calculate, or we know. So let's just write other here. N equals 1.34. We've been given that. Pi equals 3.14. I know, what a weird coincidence that these numbers use the same digits. Lambda is KL divided by R times the square root of Fy divided by pi squared times E. This is derived from the critical buckling equation. There was a way we could do it where we could go through and calculate the critical buckling and then figure out the stress associated with the critical buckling. Or we can do it this way. I'm going to recommend doing it this way. And so just follow along. You'll see what I'm going to do. Let's calculate this critical buckling. We know K is 1. We know our length is 4 meters. Now, just a second here. Look at this. We have E in this equation. E is in MPa. If we're doing something with E in it, E, or also look, Fy is in MPa. These are in newtons per millimeter squared. So that means everything else has to be in newtons and millimeters. So our length wants to be in millimeters. So we've got KL divided by R. Well, R we know, we looked that up from the member properties. Or 24.4 times the square root of Fy is 350 divided by pi squared. We can use the hard button for pi, or we can type in 3.14, it's up to you, times 200,000 MPa. All right, if you're bold, you can plug this all into your calculator, or you can do it in steps if you want. So we've got 1 times 4 meters divided by 24.4 times the square root of, and I'm going to put in brackets, 350 divided by pi squared divided by 200,000. Well, I did something wrong plugging that in. We've got 4,000 divided by 24.4 times the square root of 350 divided by pi squared divided by 200,000. And we get 2.1829. So we've got a lambda now. We've calculated lambda. We know that this has something to do with critical buckling. And critical buckling governs the design of a column if it's really tall. Squashing, this part of the equation, governs it if it's really short. We don't know what really tall and what really short means, but it's somewhere in between there. So let's now see if we can plug things back into our overall equation. So we have CR equals our reduction factor, which is 0.9, times our area, which we've looked up in our member properties of 741, times our yield stress, which is 350 MPa, times 1 plus lambda, which was 2.1829, to the power of 2 times, well, we know that n is 1.34, and then all of that is to the power of minus 1 divided by n, or 1.34. Now you can calculate this in steps if you feel like. I am going to live on the edge and do it all at once. Well, no, I might do it in 2 stages. So I'm going to start with this. So 2.1829 to the power of 2 times 1.34. And then I'm going to add 1. And then I am going to put that to the power of negative 1 divided by 1.34. So now I've got all of this component done, and then I'm going to multiply all of this times this, or times 0.9 times 741 times 350. We calculate that CR equals 44,910 newtons. Well, once we're in forces, we needed to work in newtons and millimeters because in this equation there was E and stress. But now we can convert this to kilonewtons. 44.9 kilonewtons. Well, let's take a look. CR equals 44.9 kilonewtons. That is greater than 23.3 kilonewtons, which was our CF. Woohoo! Let's give ourselves 2 big check marks. Our HSS 64 by 64 times by 64 by 64 by 3.2 works for those loads. So we have something that works here, which is fantastic. Let's take a look at our column tables. So we did it out the hard way there. Let's take a look if we were looking at the steel column tables, what we would get. So we have, we're talking about our factored axial compressive resistance, CR in kilonewtons, for a square HSS, that's 350W, using a reduction factor of 0.9. We have an HSS 64 by 64 by 3.2. And we have a beam that is or a column that is 4 meters tall. Let's come over here. The beam selection, or the column selection tables has a CR of 45 kilonewtons. They just rounded that 44.9. So they're the same answer. We did it. We checked it, and we got an answer. Now, just for fun, let's take a look and see what our sizing guidelines would have told us. Remember, the sizing guidelines want to make sure we leave enough room in a preliminary design to not be blindsided by needing something bigger than we thought we needed. Smaller can be pretty good. We don't want to be too much smaller, but it's all right if we're smaller. The sizing guidelines kind of want to make sure we don't end up needing more space than we have. So sizing guidelines for a column is D equals H divided by 20. Our height was 4 meters. Remember, this is what we worked out last term. This is the sort of thing we worked on. 4,000 divided by 20 equals 200. That's not quite far enough. Had we been doing a preliminary sizing guideline, we would have recommended as a placeholder on the drawings that you put in an HSS 203 by 203. But it looks like with our very light loads in this requirement that we can end up with a smaller column. So we're pretty good. This would have gone out on the preliminary drawing set, and then once the engineer was involved, they would have said, you know what, you can get a much smaller column here. You can get your HSS 64 by 64 by 3.2. Let's see if maybe there could have been an even smaller column. So let's go to the next page on the column charts. So this is still the column charts. That was the smallest 64 by 64. So let's look at a 51 by 51. The first one is by 64. We had a 4 meter tall column. Look, there's no compressive resistance here. This means that our KL divided by R at 4 meters was greater than 200, meaning we're not allowed to use that column at all. It doesn't matter if we calculated out a compressive resistance for that, we're not allowed to use it because our KL divided by R is greater than 200. So we had 2 different columns they wanted us to check out. They also wanted us to check a W150 by 30. Here is the good part about this. Everything we did to figure out the loads, that stays the same. What member we're using does not change the load. We've already figured out the dead load, we've already figured out the snow load, we've already figured out the factored load, and we've already figured out the tributary area, and the load on the column is 23.3 kilonewtons. So now we're just doing the same thing, but for a different member. We now want to find CR of a W150 by 30. And remember, our length is still 4 meters. Our equation for compressive resistance does not change. Our reduction factor times our area times Fy, and that governs if our column's a little baby tiny short column. But if it's tall, and we don't know what short versus tall means to a column of this size, so we'll calculate it out. But if it's really tall, buckling governs. And we know that this portion of the equation is derived from the critical buckling load. So let's take a look at our steel properties. Our reduction factor stays the same. Fy is different here. A W section is a rolled section. We're going to use 345 MPa. Remember, it was 350 steel, but in the process of heating it up and rolling it into its shape, we end up with a slight reduction in our yield stress. And E, we know for steel, is 200,000 MPa. Let's talk about our member properties. So our member is a W150 by 30. Let's go to our steel section chart, and let's find the section we're looking for. These are channels. Oh no, those aren't. Those were pile columns. All right. W shapes. We've got W shapes. We're looking at a 150 by 30. So look at this. We've got a 150 by 30 here. And we've got properties here for everything. So look, we've got a nominal mass and a theoretical mass. They're pretty darn close for our W150 by 30. 30 is the nominal mass and 29.9 is the theoretical mass. When you were doing the assignment, I had to pick one that you were entering, so I picked the theoretical mass. So pay attention to that because it's going to look for that as the exact answer. We've got our area. If we were doing bending, look, we've got our SX and our SZ. We also need to know, but that's not what we're doing right now. We're doing columns right now. We need to know our area, and we need to know things about this critical buckling. Now, remember I said that these things are going to try to buckle in the weak axes. So we orient things for bending this way because they behave nice in bending. So that means we're not going to be about the XX axis, which is the strong axis. Buckling tries to happen about the Y axis. So we're going to need our 150 by 30, that is IY and RY. Now, IY is if we do the critical buckling load calculation full out, and RY is what we need if we do the lambda shortcut version. Let's write both out just because we can. Let's get in the habit of writing that out. It gives us the opportunity to do it either way. So our member properties, our area, we looked up for our W150 by 30, is 3,810 millimeters squared. IY equals 5.56 times 10 to the 6 millimeters to the 4th. Remember, this is weak axes. because it's the YY axis. And R is going to be the RY as well, 38.2 millimeters. Our length is 4 meters, but we know we're going to be ending up talking about this in millimeters. So 4,000 millimeters. And K, I've told you I'm only going to give you examples where K is 1. But that is the effective length factor that we would apply to it. And the other things we know here, we know that N equals 1.34. We know that pi equals 3.14. And we know that lambda equals KL divided by R times the square root of Fy divided by pi squared E. So let's start right off by calculating lambda. We know that K is 1. We know the length is 4,000. We know that R is Ry, and it's 38.2 because this is trying to buckle in the weak axes, times the square root of 350 divided by pi squared times 200,000. And we can plug this into our calculator. We get, you know what, when I do it in the example here, I use 3.14. Oh, no. Do you guys see what I did? $345 MPa. We're talking about hot rolled steel here. So I'm going to come back into my equation here and change that to 345. And I get lambda equals 1.384. Now, do you guys remember that our other example, we had 2.1829. So this is a smaller lambda. Let's calculate out CR now. Well, we know our reduction factor is 0.9. We know our area is 3,810. We know Fy is 345. I'm not going to make that mistake again. Times 1 plus lambda, or 1.384, to the power of 2 times 1.34, all to the power of minus 1 divided by 1.34. So we can plug this into our calculator now. Let's go through this process. All right, I'm going to start here and work out from there. 1.384 to the power of 2 times 1.34 plus 1, and then that is to the power of negative 1 divided by 1.34. So we have 0.402 times 0.9 times 3,810 times 345. And we get 475,769 newtons. Again, once we're talking about force, we like to put it into kilonewtons, or 408 kilonewtons. we could probably just say 476 kilonewtons would be pretty darn accurate. We could round it up to that if we like. Let's look at the table, the column tables. Let's go to the column tables for W150 here. Steel column table. So that's a W360. Oh, that's not where my button is. Oh, look, there we were. W150 by 30. So that's what they asked us to check. And we have a column that's 4 meters tall. Look at that. CR equals 476 kilonewtons. So we calculated that right. Looks like we know what we're doing. But CR, so we have some good news. This is good news. CR equals 476 kilonewtons is greater than our 23.3 kilonewtons, which is our CF. So it works. But 476 is a lot greater than 23.3. Maybe there is a better column available. Let's take a look. So if we look at these tables, we have a W150 by 30 is what we had. Oh look, a W150 by 22 has 295 on it. It could take 295, but that's the last column there is. So maybe W150 by 22 is a better choice. So here, I don't know why the architect asked me very explicitly to check a W150 by 30. Maybe there's an aesthetic reason that they like that one. Maybe the contractor said that they have a free one sitting on the site already. Or maybe they didn't know and they picked it not understanding. So my job is to tell them it works and not tell them they have to change it, but to say, hey, maybe you want to go with this lighter member, because remember, this is a 150 by 30, which means it's heavier than the 150 by 22. So maybe you could save some money by going with this one. So I let them know so that they can make their decision. I don't know what their governing design criteria was in that selection. So we've gone through that calculation. It's all worked out here for you as well. So the things I want to talk to you about, and I can probably even pull this down right now. Ooh. Sorry for the weird view. Put some light back on. Darker out as we've been doing this. Oops. So the things you should know is that buckling and slenderness are related. So if you pick a slender column, it's more likely to buckle. So you want to be aware of that. Stocky columns are more likely to be governed by strength. Slender columns are more likely to be governed by buckling or their weak axis stiffness. What you should know going forward, you should know the reduction factor for steel. You should know E. You should know the value of G, but I will give it to you in the exam, don't worry. You should know Fy, which is 350 or 345. If it's different, I would give it to you. But pay attention, there is a question in the assignment where you have a different Fy. Because in the past, they didn't make steel at this grade. So I have provided you a steel grade from an old building that you're trying to check. You should know how to calculate TR for columns or braces, anything with tensile load on it. You should understand what the interaction diagram of squashing and buckling for columns look like. It is a very good exam question. You know how I like pretty diagrams. So that makes a very, very good question. Maybe, I don't know, label. What is the squashing load line? What is the critical buckling load line? What is the compressive resistance line? That sort of thing. You should know how to calculate CR for columns, but you should also know how to look up CR for available columns. So the reason in the assignment I give you an example from an old building is because the tables wouldn't apply, because we wouldn't have that. That's not current information, so you would have to manually calculate it. So it is not unreasonable that engineers do sometimes still calculate that out manually. So this was a long lecture. There was a lot thrown at you, but you finally have some answers. You can say, yes, this column works. Next week, we're going to do the same thing, still with steel, but we're going to do it with bending. So we'll do a couple examples. We'll take it slow, so we might use up the full 3 hours, but there's not a lot of lectures over the full 2 terms that we do that. So I said in the very first lecture last term that most of them will be shorter, but there will be a few that we push right to the limit, and those are the few right now. So if you need to take a break, you can pause the video, come back to it when you want. So that's one of the good things about this. We used to do this in real time on a chalkboard, trying to scribble all this in as quick as we possibly could. So I'll see you next week when we talk about steel bending.